Hello everyone, my name is Gina Lonati and I work for the Marine Mammal Center in California. I'm excited to share some preliminary results from some work I completed with the New England Aquarium the past several months using data I collected during my PhD at the University of New Brunswick. I would appreciate if attendees did not share content from this presentation without prior permission. I'll start with a quick and hopefully painless physics lesson about infrared thermography, or IRT. By definition, IRT is the acquisition and analysis of the thermal energy that naturally radiates from objects using contactless sensors. It has great advantages in wildlife science because you don't need to manipulate a subject and it doesn't require light. In general, hotter objects release more heat than cooler objects, and note that thermal radiation does not penetrate through water. When an IRT camera is radiometrically calibrated, it can convert the amount of heat received by the sensor, known as sensor intensity, into an absolute temperature. The following are thermographs of several different terrestrial species to show how IRT has been used to monitor health. This includes reproductive state in rhinos and elephants, diseases in wolves and raccoons, and injuries in hippos. Studies with IRT in whales are rare because of the challenges associated with calibrating the technology and sensing heat in dynamic aquatic environments. Despite this, IRT is already being used to detect whales by their hot blows to mitigate vessel collisions. Colleagues and I have also used IRT to describe the cranial heat loss patterns and quantify the temperatures inside the blowholes of North Atlantic right whales. I should also mention that there are many IRT studies on various pinniped species that can facilitate comparisons of heat signatures across marine mammal taxa. A paper published last year used infrared thermography to detect blunt force trauma in animal abuse cases, where underlying lesions presented as cold anomalies within 1 hour of trauma and hot anomalies approximately 24 hours after trauma. This begs the question, could drone-based infrared thermography be used to detect sublethal trauma, disease, or pregnancy in free-swimming whales? However, due to the paucity of information about thermoregulation in baleen whales, we first need to understand what a normal heat signature is. Therefore, the goal of my work at the New England Aquarium was to characterize the variability in heat signatures from the bodies of North Atlantic right whales. During my PhD, I conducted drone flights over right whales in the Gulf of St. Lawrence. During flights, I collected simultaneous IRT and visible spectrum video. For more details, please see our paper published last year. Whales were then individually identified using the North Atlantic right whale catalog. Thanks to an incredible amount of work completed by Kirkeslin McDonald as a summer student at UNB, 40 flights, including 96 IRT videos, were processed for my thesis. While reviewing the imagery, Kirkeslin made note of at least 35 whales in 43 videos with unique heat anomalies. For this pilot study, I decided to start with this subset of videos and have processed 21 videos of 17 whales to date. Accordingly, this study was designed to describe thermal signatures when heat was present and does not necessarily quantify presence versus absence of heat. Briefly, I re-reviewed IRT videos, looked for bright white patches that stood out from the darker background, identified the start and end frame for each patch, described the shape and anatomical location of each patch, saved representative screenshots or video sequences, sketched the patches, for example, see this sketch on the right, and marked each patch to extract sensor intensity metadata from pixels later. I identified almost 100 heat patches across the 21 whales, and here is a gallery of 32 of them. Feel free to pause the video when it is shared after the consortium to have a closer look. In all cases, the patch persisted in the same location as the whale moved through the field of view, indicating that the heat was not an artifact of viewing angle or reflected solar radiation. Most patches were visible on the mid or caudal dorsum, which is usually exposed to air for a few seconds during a surfacing. More caudal patches were usually only visible upon a fluking dive. The flippers and the ventrum were not visible above the water for all whales, so the relatively lower numbers do not necessarily mean that heat is not lost from these body parts as frequently. Most heat patches remain consistent in shape and intensity across multiple surfacings up to 5.6 minutes. When comparing heat signatures to visible imagery, patches did not seem to align with any obvious lesions or scars, and here are just a couple of examples. A handful of whales were observed on multiple days, including number 3812, nicknamed Nimbus. There are similarities between the heat signatures, such as the sock puppet shape on the mid-dorsum, but the shape on the cranial dorsum differs, and there are additional patches around the peduncle during the second encounter. In addition, we observed one acutely entangled right whale, number 4615, nicknamed Hercules, that was seen earlier in the day without an entanglement. As this side-by-side video plays, I'd like you to concentrate on the bright, uniform heat coming from either side of the vertebral column, where the whale seems tensed. Also note the open bleeding wounds around the tail, where there is surprisingly no significant heat. Regarding reproductive state, colleagues and I had previously observed a pregnant North Atlantic right whale skim feeding in Cape Cod Bay that had a particularly bright heat patch on its caudal dorsum. We wondered if pregnant females might have different heat signatures than other demographic groups. There were 2 pregnant whales in the dataset I collected in the Gulf of St. Lawrence. While Snow Cone had a small patch on her caudal dorsum, War did not. Caudal heat patches were observed on other non-reproductive females and males too. You may be wondering how much warmer heat patches are compared to the surrounding skin and water. To address this question, I've so far extracted maximum temperatures near the center of 33 heat patches from 6 whales. I compared these maxima to the minimum temperatures within a 200 pixel radius, which I'm currently using as a coarse proxy for background skin temperature. On average, patches were 2.3 degrees warmer, and absolute temperatures of patches ranged from 15.1 to 17.6 degrees Celsius. These are smaller temperature differentials than I expected, knowing that heat patches on seals associated with thermoregulation can be at least 10 degrees warmer than background fur. I think an important consideration moving forward with these analyses is that the visual color scale will stretch based on the range of temperatures in the field of view. This may bias us toward identifying heat patches with small temperature differentials when the body is mostly of uniform temperature, and perhaps establishing a threshold for temperature or sensor intensity differentials would be more robust. There are still many lingering questions, including how stable these heat patches are over time. Could they last hours, weeks, or even months? And what is the source of heat if it doesn't necessarily align with visible lesions? Most likely, it is non-pathological heat radiating from parts of the body that are selectively perfused or receiving blood flow. In this regard, heat signatures may provide a good window into a whale's activity state, and more behavioral context may be needed. Heat signatures may still be diagnostic of pathologies, including blunt trauma, inflammation, or bruising, but maybe we just haven't observed a whale with such injuries yet. In the case of Hercules, it is possible that the wounds were so acute that they didn't exhibit noticeable heat, like the case of the dog with lesions less than an hour old. In terms of other diagnostics like reproductive state, I did not observe an obvious pattern across the pregnant whales in my data set, though more observations are certainly needed. Next steps include reviewing thermal videos that were not in the original anomalous subset, a more thorough quantification of temperatures, measuring the size of heat patches and perhaps quantifying percent coverage, and supplementing observations with live or fresh dead stranded cetaceans. I would like to extend a big thanks to my co-authors and collaborators and acknowledge funding sources and permits. And I look forward to answering questions and seeing you virtually at the consortium. Thank you.